Okay, well, good morning, if it is morning when you're watching this. Otherwise, good evening. It's morning for me. So, apologies for being a little late for posting a video. I will try and get these out in a little bit more of a timely fashion. Starting a quarter is always a little bit more chaotic than normal, especially during COVID season. So, off we go with kind of our first kind of intro chapter into wireless and mobile systems. So, a couple things to kind of highlight here is one, I do really like this book. It has a lot of really good information. It's a bit of a dry read, not gonna lie, but there's a lot of really cool information in relation to wireless, specifically because it focuses on how cellular, for the most part, works. So very applicable. And a lot of what we utilize in this side of things also directly applies with how we utilize wireless on our internal systems as well. So a fair amount is directly applicable to a certain degree. And that's the kind of nice thing. The one, again, warning with this book is that there is a lot of math. A lot of math in there. We are not going to be dealing with any of it, so just let it wash over you in a wave of mathiness. It is not anything that we have to focus on. Our goal here is to look at the specific concepts and highlights of the actual applications of cellular and wireless and mobile systems, and then have a better understanding about how it works as a whole. So really, this book was made for electrical engineers. So again, don't feel like you need to understand the math in this, but it's still good to kind of note. So again, I will try and keep these lectures in under or about like half an hour to 45 minutes total, just so that you're not sitting there watching and trying to listen to me talk for over an hour. I know you would love to do that, especially doing it at home, in front of your computer, where you have no way to interact with me, and I start to sound nice and quiet so you fall asleep. I'll try and avoid that, so off we go. So overall, again, cellular information and just wireless technology around has been around for a very, very long period of time, but it's only been recently in the late 1900s where we really started to see a huge technological boom and everything. You can see right here how quickly things have kind of been changing across those years, and as it keeps going, it's practically every year, or in this case multiple times a year, where new technologies kind of or big events have kind of occurred. I'm not going to go over this stuff. Feel free to read through it. That's okay. So the important thing to kind of understand is with cell phone coverage and how kind of cellular data works as we're kind of going through. You can kind of see through this little infographic here that when I'm driving from one location, say Cincinnati, over to DC, I'm not attached to a single base station or cellular tower as I'm driving across over to that different location. As I move across the freeway, I move out of range and switch over into different specific areas. Now, why we use and why these are kind of in why these are in hexagonal shapes, kind of like a little honeycomb, is because that's the best average size of that we can typically utilize for calculating out the overall coverage of a particular base station. So let's take a look at something. So how it typically works is if we have, say, a base station that's set up right here, Sorry, I'm using my mouse to draw this, so it's not going to be pretty. But if we have a typical base station, our overall power output of what we optimally think we're going to have is something like a circle. That's the general gist of what we are preferred. So that is the optimal method of kind of setting. Now, the other method but how our signal is actually kind of sent out is, there's different geological issues that might kind of crop up as we kind of go through things. So there might be issues along the lines of, say, trees or general canyons or mountains. Those are types of things that affect signal. So our actual signal power that we get is probably something like that. Yeah, just on example. So that's what we get actually. So obviously this shape is going to be really hard to calculate, and so it's going to be very, very difficult for us to kind of get a better idea. So what engineers have done is to utilize, okay, well, if we can't get our optimal shape, and this is our actual shape, what's the average coverage that we typically have? And that average coverage is a hexagon. So this is our estimated. So hexagon is our estimated coverage of what we typically have, and so that's what we try and base a lot of our shaping off of, and that's why you kind of typically will see you'll see very frequently this hexagonal pattern for these base stations or cell towers that you see as you're kind of going through. So as we kind of move across to different locations, I may or may not lose coverage. Again, this is estimated coverage while I'm in the range of that specific area. As I move from, say, one base station over to the other, how do I know how to do the handoff between the two things? And there's a certain signal strength relationship that typically will state, right, if I get below a certain level, then and as the second base tower gets stronger, then my phone should automatically switch over. This concept of kind of the switching between different base towers is pretty much identical to what we see with what we're dealing with wireless networks as well. So if I have, say, like a mesh network for a business, when I have, say, a building and I have multiple different locations or access points that are kind of set up, as long as all of the different access points are on the same SSID, then I should, in theory, be able to walk around the entire building or campus and still maintain access to my wireless, and I only have to log in once. So how does that work? Well, again, there's a specific handoff that occurs at different points. And it's all based off of your signal strength. The thing with it, though, is that sometimes the handoff occurs at the cell phone level, if we're talking about cell phone, or the device level that is actually connected up to the access point itself. So it's typically not done by the actual cell towers or the wireless access points to a certain degree. Now, there are times where, say with like Cisco Meraki, you can actually set it up so that if someone drops below a certain level of signal strength, that access point will just automatically kick them off, and it kind of is a way to force a handoff. So we do have ways where it can actually where the access points, and that's similar in concept. If the signal strength drops too low on a cell tower, it will just automatically boot the person off of that cell tower in order to get them to kick over to another one, generally. So hopefully that kind of helps kind of explain a little bit of why we use kind of this hexagonal pattern, and gives you at least a rough idea of kind of how we're kind of moving through. So again, I'm not going to go through the history of stuff. Feel free to read about that yourselves. It'd be me just reading, and that would be boring for you. So we are going to move on to kind of additional things. But one of the things I'm going to talk about here quickly, though, is just how quickly technology has kind of advanced and how much everything has kind of grown forward. So, 1G was really when things originally started. 2G was where things started to really start to ramp up in late 90s. And then 3G is when it really took off. In fact, you can see the big trend is around like 2005, 2006 is when a huge number of subscribers really ramped up and just kind of continued. That time was around when the first iPhone was released, so that 2004 to 2006 range. I can't remember the exact year, but that's kind of the big boom was iPhone to a certain degree. So looking at kind of other types of kind of communications and stuff, one thing to kind of note is we do have different types of cellular coverage as well. We have things in our cellular coverage is good to, or satellite coverage is good to know the different types of sizes that we're looking at, and then how they kind of correlate between different things. So we have, say, a picocell coverage that relates to a single or multiple buildings. We have a microcell that relates to kind of an urban setting, so think of it like a city. A macrocell, well, suburban area, so a little bit more wide and open. And then a global, which is just that, it covers the entire globe. So I hate this slide. It looks like the 80s or 90s kind of just vomited into a chart. It is not a great slide. But essentially what they're trying to illustrate here is a transmission capacity. So basically they're trying to show that on our axis right here, we're looking at mobility. So the up and down arrow axis. So we're looking at mobility here, which is basically how fast we're actually moving. So if I'm stationary, I'm likely going to get pretty good, or assumed, faster data rate, versus if I'm walking or if I'm moving very quickly, such as I'm in a car or a train. So essentially what we're looking at is the different types of potential systems that we utilize for actual data rate here. And so if we're, say, in like a vehicle, we have broadband radio, so just what you might listen to in your car. That's kind of outlining what your estimated data rate is actually going to be at, say, moving very quickly, so about like half a meg to 1 megabits. Where if we're standing still, potentially, theoretically, we can get much higher, up to say like 100 megabits. So that's basically what we're trying to get across with this system, is to just understand that if you're stationary, odds are you can probably get better data. Depending on where you're standing, stationary, you can likely get a better data rate versus if you're driving very quickly. You're probably not going to have as good of a data rate. So why is this important? Why do we really care? Self-driving cars is a very big, it's one of the new bigger technologies that's coming out, especially self-driving semis. One of the things that they have to kind of figure out is to be able to send large amounts of control data back and forth between a semi and a specific control station, and we're talking about tens to hundreds of gigs of data that has to be transferred continuously back and forth over the course of a specific drive. if not more than hundreds of gigs of data. We're talking potentially terabytes of data that needs to be transferred back and forth between a vehicle that's self-driving and a control station where we can actually monitor the situation of the semi itself. There's a lot of information and data that has to go back and forth in kind of a general control structure. So how do we do that? Well, we're working on it. So a lot of the different types of things that we'll be looking at is cellular, wireless, LANs, and PANs. PAN is personal area network. So LAN is local area network. GPS related, satellite based, home networks, ad hoc networks. So wireless technology can essentially be applied in a lot of different ways. One really cool way is sensor networks, where we utilize wireless sensors to basically send us alerts. An example of something would be like, smoke detection. Oops. Let's clear my canvas. So if I have, say, like, multiple different sensors, and essentially there's a big smoke cloud, spooky smoke, ignore my drawing, as the sensors see that there's a specific smoke coming in, based off of kind of air filters or air sensors, it sends a signal, and then those signals get essentially beaconed out to other sensors within a range, and then they get sent over to other devices, which eventually gets sent, I'm trying to draw waves, over to a control station, a primary location that it actually understands and says, oh, there's a smoke cloud coming away, and it hit sensor 1, 2, and 3 within a given period of time, so I can calculate when it's going to hit sensor 4, when it will hit sensor 5, 6, and 7, and I'll know when that smoke cloud is going to come and get me. So wireless sensors are awesome. They're really cool with what we can kind of do. So how can we use wireless information for kind of LANs or kind of PANs potentially as well for kind of medical care? So a lot of what we can do is we can utilize pretty much cellular in all aspects. So if there's a physician that's working on a specific patient, and they're not exactly sure what to do, or if they need some additional help or consulting, they have their specific, that little kind of Y is a antenna. They call out from their specific phone, goes to a broadcast base station, so the cell tower, which goes to mobile carrier control center, which then gets sent over to, say, like the IP or ATM-based backbone network. So however Verizon or whoever owns the network is kind of set up. And then that can go down to, they're skipping a few things, but to, say, like an access point where there's a remote consulting kind of agency that sets up and is able to kind of view along those areas. So don't worry about these types of things, but this is the cool part, where how we can make a phone call and it goes over to the other area and back. And so if we're utilizing cellular systems, that's kind of the important aspect to kind of think of. So so I kind of already explained this as well. So again, of our base station here, you'll see BS a lot. It just means base station. Again, the hexagonal pattern is essentially the estimated or best estimated shape of the signal strength that we typically have. Okay, so let's look at the different types of kind of frequencies that we can utilize, and how far we've actually really come. So with wireless frequencies, Essentially, one of the very initial ones was FDMA, which is Frequency Division Multiple Access. So essentially here, what we're talking about is that each user that is connected up to a specific base station is given a specific unique frequency to sit on, and that's how they actually are able to intercommunicate. Now, the issue here is we only have a certain number of frequencies that we can actually allocate out, so therefore we can only have a certain number of users to actually connect up and over. And once I hit my limit of n, I'm out of frequencies, so therefore I'm out of users as well that can connect up to that base station. So if you want to equate it to something that you know, kind of think of it like IP addresses, right? I have 10 IP addresses available to me, or public IP addresses, so therefore if I have 10 users that go out to it with just static NAT or dynamic NAT, that's it. No other accounts can go out or access can go out until one of those 10 users is done with their IP and gives it back. So same thing, think of frequency in this case as basically being your IP address. So once I hit my limit, no one else can go out. So that's kind of that was a very old and initial structure of kind of how we have it. So this kind of just hopefully gives you an idea of users are on their mobile stations, MS, connected up to a base station, BS, and so each individual user gets a specific frequency, and then until they drop off, once I hit my hard limit of n, then there are no more frequencies available, and no other users on mobile stations are going to be allowed to connect up to that base station, even if they're standing right next to it and can get really good signal strength. So we had to figure out a better option than that, because obviously that's not very efficient. So one option that we started that was kind of a fix to it to a certain amount was TDMA, Time Division Multiple Access. So with this, essentially how it would work it would allow us to split up users across frequencies across time. So users would basically share the frequency that we're utilizing across a given point in time. So there's a better option, or here's a better kind of illustration of what it kind of means. So user 1, user 2, and say user 3 all are sitting on the same frequency, but they're sharing time on that frequency. So user 1's allowed to send, then user 2's allowed to send, then user 3's allowed to send, and then so on and so forth. This is essentially very similar to how wireless access points typically work. So if we look at how wireless access points work, you know, if I have my, gosh, I apologize again, writing with the mouse is hard. I have my access point. So this is my wireless router that's kind of set up. How it works is it is essentially just a cop. I shouldn't say a cop. It is basically essentially just in charge of keeping time for everyone. So, and what I mean by that is, let's say that we have an access point, and let's say this crudely drawn circle is its range of wireless access. Well, if I get on with my cell phone here, and then someone else gets on with their cell phone over here, so we'll put a little T there for me, and we'll put X there for someone else. Well, if we look at that, my cell phone has a specific given transmission range or power range as well. I might only see something like that, and the other cell phone that just walked into the access point range might see something just like that, where I know I overlap those lines a little bit, but I'm bad at drawing. They're not supposed to overlap. So we might not be able to see each other based off of our signal length, but we can both see the access point. So how do we know when I'm allowed to send data up to the access point and then go out to the internet, or when user X is allowed to connect up to that access point and send out? Well, the access point is in charge of basically keeping time and basically kind of being that person that's controlling traffic. So it goes, okay, well, I send a request to send message, and then until I see a message back from the access point that says I am clear to send, I will wait. So I will wait until it's my turn to actually send. And same thing happens with user X. It will continually try and beacon out and go, hey, I'd like to send data. Is it my turn to go? And the access point will basically be in control of going, okay, well, now it's Travis, you have the next, half second to send as much data as you want, and then user X, you have the next half second to send data as quickly as you want as well. And so we share time on the access point itself in order to both send it. This is why, if you ever go to, say, like typically really crowded areas, and they're offering free Wi-Fi, and you try and get on it, and it's like, well, this is terrible. I say, if you ever go to crowded areas before COVID, this is why access points, have a hard limit on the number of users that they can typically support. I remember going to CenturyLink Stadium. I think they renamed it to Quest for a Seahawks game, and they have free quote unquote Wi-Fi available there as well. Well, I got there super early on the game, so I could watch the Hawks run out onto the field. And when I was there super early, the stadium was pretty empty. I could connect up to their Wi-Fi that they had, and I could browse Reddit while I waited, and it worked great. Everything was happening, no issues. But then, as it got a little bit further and further in, and more people started to show up, things started to slow down because everyone started to jump on that free Wi-Fi. The access point got slammed, and it was trying to split time, but instead of between me and say 50 other people, it was trying to split time between me and say 5,000 other people. It just doesn't work very well. So there are hard limits for basically how well an access point can process how and send requests back and forth to say, here you go. So hopefully that helps kind of explain TDMA a little bit. So TDMA, definitely a big improvement from FDMA, but we could do better. So enter in CDMA, Code Division Multiple Access. So what does this do? Well, if we were using frequency and time, now let's use codes. So essentially, this just allows us to have even further number of potential users on a single given frequency. So essentially, what this does is it allows us to, instead of having users 1 to up to n all having to split time across a given frequency, now what we're able to do is say, okay, well, user 1, 2, and 3, we're going to make unique, essentially, frequencies. Well, you'll all be on kind of the same frequency, and you'll all be using that at the same time, but we'll make all of your signals unique to each other by changing the code in which you're transmitting so that you don't have any overlap across each other. So here's kind of an example of what it kind of looks like. So we have our informational bits of basically this is what it looks like. There's a 1, 0, -1, whatever, across the line. Well, then we apply a code on our transmitting side to the informational bits. And essentially what it does is, after the actual transmitted signal itself then gets adjusted as we actually send it. The signal received is the transmitted signal, and then because the other end also knows what the code is that we sent, it can essentially decode the signal and then see what the actual data was across the other side. So think of this essentially as encrypting and decrypting, right? So hopefully that kind of helps. So other options that we have as well, OFDM, orthogonal frequency division multiplexing. We'll chat more about that later, but starting to hit my 30-minute limit that I said I was gonna stop doing. So another couple of things to kind of get into is frequency hopping. Frequency hopping was actually a way to kind of bypass. It was actually used in and still is used in different military sections, where essentially it's a way to stop people from eavesdropping on your signal. So if I'm bouncing back and forth between different signals each time I'm sending things, unless people know the frequency of how I'm sending the data, they're not going to be able to see, or it'll make it much harder to actually intercept all of said signal that I'm transmitting. So frequency hopping is pretty common. Kind of gives you an idea. All right. So early wireless systems. Basically, what we were looking at is the very early systems were essentially, let's build a really, really tall tower, slap a bunch of antennas on it, and run a whole bunch of power through, and just broadcast out as big of a service area as we absolutely can. Doesn't always work that great. And in fact, it was very inefficient, and as you got to these outer sections, overall the signal strength was very, very weak. So again, this gets us to the other option that we typically utilize, which is kind of this small zone system, where we use that hexagonal pattern in order to kind of create a honeycomb shape of kind of overlapping signals. If you've driven around Seattle recently, driven from Bellingham down to Seattle, or Seattle up to Bellingham, if you pay attention, once some of the areas that you're passing, you'll start to see a whole bunch of, like, every quarter mile to half a mile, you'll start to see some cell towers closer to the city, right along the freeway. And it's pretty easy to tell. They're just a straight line with really actually kind of that those flat antennas for you to kind of see. And that kind of again, they're for different wireless providers as well. So they're not all, say, Verizon or all AT&T, but they essentially are utilized as kind of and set up in that kind of honeycomb pattern for overall service. So what we kind of see here with this kind of setup is this is very, very broad of how we kind of look at it. So we have your mobile station, which is your cell phone, base station, which is the cell tower, base station controller, and then mobile switch controller, and then or system controller. And then that gets up to the public switch telephone network, which then goes to, say, like the home phone itself. So again, very oversimplified of the general network, but this is kind of the general setup of how most networks are, cellular networks work. So how things are kind of set up, request for downlink control channel, and then sending downlink traffic control channel, and then I can actually send control data. All right, getting pretty close to. So here's essentially, again, kind of just a quick walkthrough of how a call setup works between a base station and a mobile station. So mobile station says, hey, I need to connect up to you and send and make a phone call. So sends a request to say, hey, I need to establish a path. The base station says, cool, here's how we're going to be communicating. So we're going to be utilizing FDMA, TDMA, CDMA, whatever, as our method of kind of communicating. One thing that's important to note about FDMA, TDMA, or CDMA, or other types of methods, is how we're communicating is essentially at layer 1. So this is determining essentially the how I'm sending the actual data itself out of my antenna. So this is layer 1. These are all dealing similar to, say, like, if it's electrical impulse or lights like fiber, that's all at layer 1. FDMA and these other methods for frequency for wireless signal are layer 1 as well. So after we know that information, control information is sent and an acknowledgement sent back, and then it says, okay, now we can start communication back and forth between these areas. So I kind of did want to skip a few there, a little bit of movie magic, just because there was some slides I didn't want to really click through. If you do have questions on those slides I kind of skipped over, feel free to reach out whenever. But the kind of tail end, or last thing to kind of focus on here, is, again, the wireless sensors, which are, again, pretty cool, and give you an idea of how they kind of are set up. So a sensor is basically just a lightweight, sensor. It's a lightweight device that has a specific given radio frequency range, or radio range, and typically you'll place them within a given range of each other, and so that they'll all be overlapping. So when a specific event occurs, it goes, hey, I know that this issue just happened, such as, say, like cloud smoke, and it will relay that information to a nearby sensor, and then that sensor traffic will be sent down towards, say, like a data collection device. We'll get more into them. They're really cool, and they're also used pretty commonly in, say, industrial control system environments as well. So, alright, that's about it, grand scheme of things. So if you do have questions, again, feel free to reach out. Hopefully that was helpful for you guys, and I will talk to you later. Alright.